Now we want to run something called observing method. So this is another way to obtain optimal structure. So before we use this regularity lemma and blob lemma to obtain spanning structure. And one downside of this regularity method is that it requires n to be huge. So n has to be at least 2 to the 2 to the 2 to the 2 to the tower type bound that you get from the regularity. Otherwise, it wouldn't work. So in terms of bounds on n, it gives us a bad bound. On the other hand, there is something called observing method, which is better in this perspective. It usually gives much more reasonable bound on n. And in many cases, I mean, this has some advantage over this regularity method in various ways. Sometimes, I mean, it's better to use this observing method to get type bound. And also, I mean, this observing method is more general. It's not just to get panning structure. I mean, usually it's, I mean, for other type of problem, for example, graph decomposition problem, can you find the exact decomposition or other things? I mean, this kind of method is useful. And what's the observing method? Roughly, how it goes is you build an observer with some good property. And whatever this observer is, and we build an approximate structure. Then we convert this approximate structure into optimal one using this observer. So name observer is that it observes the remaining vertices. So approximate structure you can consider as near spanning. Let's consider some simple example. Let's say you know your graph has minimum degree more than half times alpha plus n. You want to show that the Hamilton cycle exists. So which is weaker than Dirac's theorem. Suppose you want to prove this. And how do you prove it? Is that you randomly choose the random matching of, I mean, size, say, some epsilon n. Epsilon is smaller than alpha, say. Instead of epsilon, let's say alpha pure n. Then what happens? You have this. Then what you know is that for each vertex, it has half n plus alpha n neighbors. And each vertex here also has large degree. So there are this many vertices outside, and then each one of them also has this many neighbors. So even if you send all of them here, there must be some edges here. So there are many edges. So how many edges? Like alpha n square over 2 edges you can show. Okay, but what you know now? So this means that if you randomly choose edges, then this for vertex B, the probability that some of the edges here are chosen. So with the Cherenkov bound, many edges here must be chosen. So what do you know from this is that if you take this random matching, then for every B, say this is E1, E2, and E alpha square n, there are at least, say I, at least some number, say alpha 4 over n, let's say at least alpha quarter n choices of I, such that B is in the common neighborhood of this. Say that's xi, yi. So B forms a triangle with this. That's for every I. There are many choices. Okay, then what happened is that you have this matching and you connect it, you extend it into path. So these two vertices, what? They have a minimum degree. So they have at least like alpha and common neighbor. So you find the common neighbor and you find the common neighbor and so on. But the number is quite small. This is smaller than alpha. So let's say alpha is smaller than 1 over 100. This is much smaller. That means that every time you do that, I mean, these two have alpha and common neighbor, and then you may choose the ones that's not used because so far you have used n mod alpha square and vertices. So you can connect this to get this path. This is your observer, path PA, which is our observer. Why is it called observer? So you will see later. So no matter what vertices you take, which is at most, say, due to this choice, at most alpha to the 4 and many vertices. What you can do is for this, you can choose one edge that forms triangle with this. And then for this, you can choose another edge which forms a triangle with this, because there are alpha to the 4 times n choices, and then this set has smaller size. So you can keep choosing it. And then what you do, instead of this path, you can take this path, which uses all the vertices here as well as this vertices. So in other words, this path absorbs these vertices. So that's what this called observer. So from this, what we can see is that our plan is that you take this observer, and then in the remaining, you kind of extend this to a longer path. And then whenever you have a small number of vertices left, you observe this into this path. Indeed, that's possible. How? Now you have this, right? And then see that this is very small. This entire thing has length at most 2 alpha square n. So in the remaining graph, its minimum degree is still half plus alpha minus 2 alpha square, so alpha over 2 n. So what you do is you can find the long path here. By minimum degree, you can find the path of length at least half and here. And you again use the common degree to connect it. Okay, maybe before that, I forgot one thing. So before doing this, you have this large minimum degree. And what you can do is that you can take some random set of the size, I don't know, let's say alpha to the 10n. Then if R is reservoir, so what's the reservoir? So this is random set. So what we know is that for any, say, vertex B, we can ensure that the B has at least, say, half R plus alpha over 10 R labels in R. So using parallel bound, say, you can show it. And this has size roughly, say, this. And in the remaining one, still its minimum degree is like, since we deleted this R, it might decrease a bit, but still more than half. So here you can find the long path of length at least half n. And then again, you know that this vertex and more than half here, so they have a common neighbor here. So you have a longer path. And then here, some vertices remaining. And what do you do? And if this vertex, every time a vertex has a two consecutive neighbor, then you can replace this. You get a longer path. And you keep do that until you cannot do anymore. So you have a small number of vertices. You cannot do anymore. Then what you know? Every vertex here does not have two consecutive neighbors. So it sends almost half of these vertices are neighbor over here. And then this part and this part are smaller. So this has minimum degree at least like say this much in here. But it's sending only half to here, meaning that it's still sending lots of edges here. Using that, you can find the long path here. And then again, this and this has a common neighbor here, so you connect. You keep do that, and you can show that you can do this. And then in the remaining one, again, every time you can find the vertex, which has two consecutive neighbors in this longer path. Then you plug that in, you insert that vertex. Otherwise, again, you find another vertex and then connect it. And this reservoir is its role is to connect it. And you keep do that until when? You can show that you can keep do this until the number of remaining vertices is very small. And at the end, now this and this, you find the common neighbor here and then connect. Then everything becomes like long cycle where this part is PA, the observer that we take. And then some part of reservoir is remaining, and then some small parts remain. And you can show that this has size this much, and then this also has size small. So the remaining one has size much smaller than alpha to the 4n. Now you use the property of observer, because this observer was taken in such a way that every vertex has at least alpha to the 4n choices of that. So for each one of them, you can choose in a distinct way that can be observed. And then finally, this is our Hamilton cycle. So that's roughly how the observing method goes. So you find the observer, and then you find some legible, which helps you to connect things. And then here you find some approximate structure, and you use legible to connect. Until you do that, until a very small number of vertices remain. And those small number of vertices can be observed into your observer. Okay, so maybe to get more feeling, so this is simplified, quite simple case. So let's try to prove the following approximate version of Posat theorem. So a Posat conjecture. So for given alpha, let's just write it this way. Assume this, and so for given alpha, n is sufficiently large, but here, since we are using observing method instead of regularity, so this relation is not like humongously large n. So if G is an n vertex graph with the minimum degree is can G contains the square of Hamilton diagram. So we want to prove this. Then now we first prove some lemma. And what lemma do we need? We want to prove a lemma that gives us the observer. And then we need the proof that this kind of connection is possible. And we also need to find the legible. So that kind of lemmas are needed. And let's start with the connection lemma. And how do we connect? So let's say, K clickwork is the K minus 1's power of a path. So let's say K minus 1's power of a path as a K clickwork. So this is 2 clickwork. This is 3 clickwork. And so on. Okay, so what's this connection lemma? So suppose that you have a graph G, which is an n vertex graph with a minimum degree at least 1 minus 1 over k and n plus 1. And suppose x1 to xk and y1 to yk, each of them each of these forms a copy of k click in G. And we want to show that there exists k click walk, the W, which starts with x1 and xk and ends with y1 and yk of the length t in G, where this t is not so large, and this t is divisible by k. So this is a connection lemma. So before we have one vertex, and you can directly connect. In this Dirac example, you have half cross epsilon and degree. So you find the common neighbor. But for square of the path, let's say you have square of the path. You have square of the path. How do you connect it? In order to connect this, you need to make sure that in order to connect it, it's a bit more complicated structure. So it's not as simple as this. So you have to be able to connect it. If you just use the minimum degree in naive way, and what you know that from your condition, this is the minimum degree. So every 3 of them have a common neighbor. So these 2, you can find the common neighbor. And then these 2, you can also find the common neighbor. But what? You have to find the common neighbor of these 2. And then in order to, ensure these 3 edges, what? You need the one vertex. Okay, if you have say one vertex, which is adjacent to all 4 of these, and then there are edges between them, then then you can complete your connection. But you know that every 3 of them has a common neighbor, but the 4 of them is different. So you cannot naively just do it. So you need some sort of argument which allow us to be able to do this. Okay, so in order to prove this connection lemma, let's first prove the following claim. So let's say you have a vertex Q1 to Qk, which forms a PK. And let's say you consider a permutation, arbitrary permutation. Then we want to show that there exists a K-clique walk. Okay, I think we have made the wrong definition here. Let me change this. So we are considering walk instead of a path. So let's define it properly. This is W1, W2, W, say, S sequence such that the Wi and Wj are all adjacent if I minus j, the difference is at most k minus 1. So here some of the vertices may repeat. So as we normally say, if we have a walk, that means you can come back to where you started and then use the same edge and then go. That's also a walk. And this is as long as you have these edges. So this sequence is actually a 3-clique walk. Okay. So now what? We want to find the K-clique walk. Say W A prime, which starts with Q1 to Qk, and which ends with Q pi 1 to Q pi k. So it starts Q1, Q2, Q3, and then in your work, somehow you come back to it with a different order of the vertices. And this claim is not so difficult. How do you do it? So you have, say, Q1, Q2, Q3, say, Q4. Then what? This is K of them. And then due to your minimum degree condition, what you know is that any K vertices had common neighbor. So you know that the observation, any K vertices has a common neighbor. So what you know is that this forms a clique, and then you choose a vertex U, which is common neighbor of everything. Then what you can do is instead of Q1, Q2, Q3, Q4, and you can insert this U to say you want to swap the places of Q2 and Q3, then Q1, U, Q2, Q4. So at the place of Q3, now you put Q2, and then to place of Q2, you put U. But this is also click work because without this one is also click of size K. And then now you can write the Q3, Q2, Q4, then Q2 and Q3 are swapped. And once you know this, how to get this transposition, then you repeat. After that, let's say you want to swap Q1 and Q4, then U, Q3, Q2, Q1, then Q, say 4, Q3, Q2, Q1. So this is a K-click work. So by using this one additional vertex, you can freely take this transposition, and then at the end you can reach the order, the permutation you want to take. Of length, say, T prime, and most 2K square minus K, which is divisible by K. So you see that every time you do this, you use 4, the K of them. So the final length is divisible by K, and then technically, I mean, this part is not needed. You can directly write this afterwards and then this afterwards. And then the number of transposition you have to take is at most n choose 2, and K choose 2, then you can get this, I mean, bound. So I will not write down the, I mean, rigorous proof of this, but you already see that this is true. Okay, and then now how do you do it? You start from, say, x1, x2, x3, xk. Let's say, I mean, your k is like 4. And then you have y1, y2, y3, y4. Then what you do is you keep taking, you keep extending this. You extend this click work. And while you're doing that, you want to make sure that I mean, you count the number of edges between this and this. This K and this K. Okay, let's say there are no. And you choose the next one so that the number of edges between them are more. And here are even more. And then you keep building this. And while you're doing that, you make sure that the edges between them, there are more and more edges. At the end, I mean, there are so many edges so that we are able to use them to connect it. That's what we want to do. But how do we ensure the number of edges between them are large? One observation is that for every 2K vertices, what you know is that you can always find the vertex U that stands at least 2K minus 1 edges towards them. Why? If you have 2K vertices and you consider its neighborhood, its degree, summation of the degree of the vertices in this U is at least what? 1 minus 1 over K n plus 1 times 2K. So this is like 2K minus 2n plus, it's bigger than this, strictly bigger than. So this one also add up. Then by Pigeonhole principle, one of the vertices, so this means that averagely all the vertices is in at least more than this many of the, vertices neighborhood. So by Pigeonhole principle, there must be a vertex which is adjacent to at least 2K minus 1. Okay, then what? You can use this so that you have this K vertices. This K vertices. Let's say you have a vertex U that stands, say, 4 vertices here, 3 vertices here. Then you use this U to extend this. Then what? You extended the one of the click walk, and then now suddenly this one stands like 3 edges to here. So the final 4 and then final 4, the number of edges between them, you can kind of increase. So in order to show this, let's first say for each I, let's say y prime I with the y k minus I plus 1. So as I write here, so this one you keep extending it to this direction, but this one you want to keep extending to the left direction. So it's more convenient to write this in this way so that it starts from 1 and 2, 3, 4, and then it keeps extend. Instead of 4, 3, 2, 1, and extend, this one is more natural. So let's write it this way. So what? We choose a pair, say W1, W2, of K click walk. That W1 starts from U1 to UK, UK plus 1, UK plus A. And W2 is like B1 to BK, BK plus 1 to BK plus B. Where if UI is XI, then VI is Y prime I for the first K of them. And A plus B is say P times K. So we choose a pair. So A plus B is multiple of K. And among all the choices, or such pairs of walks. So among all such pairs of walks, and we only consider the ones that satisfy the following, where U is the last K vertices in the K clearwalk, and then B is the again last K vertices in there. And we want to only consider the ones that this holds. So what's this? So this counts the number of edges between the last K1 and last K1, and then you count the number of edges between. That's exactly this. So for each vertex U in this U, so you count how many edges it sends to V. And that's bigger than your like total length divided by K. So you choose all such work, and then out of them you choose the one with the largest P. So why do we write it this way? So every time you kind of extend by K, and you want to make sure that the number of edges between them also increase. So this one, for the longer you take, the number of edges between them must be bigger. So this has to be bigger. So if P is 1, then you don't really care. If this is like 100, then there must be at least 100 edges between U and V. And then out of them, you choose the one with the maximum P, which will ensure that the number of edges between is also as large as possible. So among all such things, you choose the one that maximizes P. In fact, I mean, this is not empty set. The collection of all such pairs satisfying these are not empty set because note that the pair x1 to xk and y prime 1 to y prime k satisfies, say, a equal b equal 0, thus p equals 0. So no matter what this is, this holds. So you consider all the pair which satisfy this, and at least, I mean, this one is there, so it's not empty set. So among them, you can choose the one with the largest P. Thus, the a choice, I mean, there could be multiple choice. You choose one of them with maximum P exists. And let's say for such a choice, so we fix such a choice. And let A be the, say, all the indices which UA plus J tends B to more than K minus 1. And then B with the indices B, E plus J, which again sends at least K minus 1 to U. So in our choice, you have this like square path. I mean, K clearwalk. And somehow we ensure that the number of edges between them are large. And for each vertex, I mean, out of this K vertex, some vertex sends more than K minus 1 edges. And then we include that into this A. And then if this sends that many, we include this to B. And we want to claim that either A is everything on this K, or so one of them has to have size K, which will be useful to connect these two K-click work into one K-click work. So proof of this plane. So assume that both of them are smaller than K. And assume Q is the number of edges between them. And we know that the U and V may not be disjoint. We know that the U and V have both size K. And using this observation, actually, I mean, here it doesn't have to be 2K distinct vertices. You can count the same vertices multiple times. As long as, I mean, so you can rewrite it. That does not send this edge, but you can rewrite it for, say, you want to use 2K or sequence of vertices. So then may not be disjoint. There is Q such that U is in neighbor of UI for at least 2K minus 1 choices of I. So let's write it this way. Then using this observation, what? There exists a vertex W which sends this holds. So U and D might be sharing some vertices. In that case, that vertex might be counted here as well as here, but it's sending at least 2K minus 1, I mean, neighbors in here. Some of the neighbors may be counted twice. And without loss of generality, let's assume that it's sending neighbors to all of the vertices in U, and it's sending at least K minus 1 edges towards B. So, as we assume that if A is smaller than K, there exists index A J star such that this U A plus J star is not in A, meaning that its neighborhood in B, it doesn't send much. So it's sending like a strictly more than K minus 1 neighbors to B. Okay, then what can we do? We want to kick this out and then put W instead. Then this one was sending to B and most less than K minus 1, but this one is sending more than K minus 1, more than or equal to K minus 1. The number of edges between increase. So we consider a W prime 1 as U1 to UA plus K. So this one is W1. And then you repeat the last K parts, except that you kick out this one, and then you plug in W. And you come to the last one, U A plus K. And then W2 is same. Then you consider a new pair. W prime 1 and then W2. What? Now your last vertex, last K vertex here is U prime, which is you kick this out and you add this. Then what? You consider the number of edges between them, and that's like at least one larger. And what's the length? And it has A plus B, A prime plus B is P plus 1K, where this A prime K is the length of W prime 1, because you attach K more over it. Then what? This new one still satisfies this condition. So this new choice satisfies this. So this new choice is the one that satisfies this condition, but it is longer than our previous choice. But that's contradiction, because our previous choice was the one which maximized this P among the ones that satisfy this. So which is a contradiction to the maximality of W1 and W2. Hence, we have that either A is side K or B is side K. Okay. So now we know this, and we have this case power of the K click work, and last K's are here. And let's assume, without loss of generality, this B is size K. Okay. And we know that the P is at most like P square, because what? We know that in here, this condition, this one is at most K square. So P is K square at most. Now you see it. So you have this UA plus K, UA plus 1, and then PA plus K, PA plus 1. And each one of them sends K minus 1 edges. So it's sending at most one non-edge, and then everything else is an edge. And this sends at most one non-edge. They may be same. It sends at most one non-edge. It sends at most one non-edge, and so on. And now we want to take a permutation. So let's say, how do you take the permutation? Take a permutation pi, so that PA plus pi give me a moment. So this one's not A, sorry, this one's B plus 1. Okay, so how do you want to do it? K, BA plus pi K minus 1, BA plus pi 2, BA plus pi 1, so that sorry, let's write it this way. This is B plus K, B plus 1. Okay, then how do you do it? You make sure that so here you permute it so that this one is sending some non-H here, then that non-H is actually here, meaning that this sends H towards everything above. And you make sure that the next one might send some non-H here, then it's sending here so that it's sending H's towards everything up. And the next one, the A plus A pi 3, this might already send non-H to below 1, then that's fine. Because all we care is this sends everything up here as an H. So you permute this in such a way that everything here is sending everything upward as an H. Its non-H is only going below. So this is possible, right? So this is already here. So for this, its non-H counterpart, you put it on the bottom. And second one, you see its non-H counterpart, you put it on the second bottom. And third one, okay, its non-H counterpart is already assigned. Then you don't have to do anything. You assign an arbitrary one here. And the next one, you see its non-H counterpart, you put it on the here. I mean, unless it is already assigned, then you arbitrarily do that. So you can take this permutation. So that with this permutation, we know that the UA plus pi 1 UA plus pi k minus j are all neighbor of this B plus j. So this one, I mean, you don't care. This one is adjacent. This one is adjacent to 2. This one is adjacent to 3. And so on. This one is adjacent to everything except on the bottom. So you can permute this. You can take such a permutation. Now what you do is you take, say, W double prime, which is you start from UA plus pi 1 and UA plus pi k minus 2, UA plus pi k minus 1, UA plus pi k, and then you repeat. But now in the new sequence, what you do is you replace the last one with the P1, P plus 1. So this is still k-click work. Why? This new one is adjacent to everything, every k minus 1 thing here by our choice. And now again, you repeat this, but now you replace one more, B plus B sub B plus 2 here. So this is again click work. Why? So this one is click. So this one is adjacent to this one as well as this one. So this one is adjacent to, by our choice, it's adjacent to all these k minus 2 things as well as the one before. So it's okay. And then this one is again adjacent to this and then everything before. And now you repeat. Now you repeat this to the B plus 3, B plus 2, B plus 1. Again, this one is adjacent to all these k minus 3, 1, as well as this 2. So you can keep do this until what? You take this. And by doing this, what? From here, you take a click walk so that the end vertices are in this order. Okay, so, and what? From our construction, it has length m mod k square. So Now what? But with this permutation, we already showed this previous claim that we can find the click work from any permutation to, the identity or original order to any permutation of this. So now what? By the previous claim, there is work a W star, which start from UA plus 1 to UA plus K, and then ends at UA plus pi 1 to UA plus pi K, such that again, length is at most 2K star minus K and divisible by K. Okay, so now what? You take W1, and whose end part is UA plus 1 to UA plus K, and then you take this W star. Then you start from here, and then you end with this permutation. And then you take this like W prime prime, which connects this with Vk plus V sub B plus K to V sub B plus 1. And you take the reverse of, W2 to W2 to the negative 1, you reverse. So this forms a K click work. And then it ends with what? YK, Y1. So, no, W2 actually ends with, this is a Y prime K to Y prime 1, which is same as Y1 to YK. It ends with it. And the total length is, if you add it, then what? A plus M 2K squared minus K plus K squared plus P plus K. And then we know that A plus B is M PK, which is like K cubed. So in any way, it's M 4 times K cubed. And length is divisible by K. But every one of them, when we are constructing them, the length is divisible by K. Okay, so now we prove this connection lemma. And now we have to prove observing lemma and legible lemma. And then we use them to prove this approximate version of Poisson theorem. And probably it's good to break our video here. It's been quite long, so in the next video, we will collect the other tools like observing lemma, and then we start the proof of this approximate version of Poisson theorem, Poisson conjecture. Okay, then in next, I will see you in next video.